Hello all, I'm back with another video, and this one is from January 2026, and it's a Unit 5 past paper. And you may be wondering, why am I uploading a Unit 5 paper again from January 2026 since I already uploaded one? So the answer is that since this past paper season in 2025, in November, they started giving out two versions of these papers. The one is the regular Unit 5 or Unit 4 and Unit 6 and so on. And the other one is called Unit 5A. Okay. I searched online, I tried to find an answer why this is the case, but I couldn't. So if anybody knows why, please let me know in the comments. And this version is totally different from the one I recently uploaded. So let's dive in with question 1 in section A. Again, the general rules I always say is that okay, a rule that I never really mention is that if you don't know something, skip it, solve the things you know, and then come back to things you know later. Then questions that reward 1 mark should take you about a minute. Questions that reward 10 marks should take you about 10 minutes, and so on and so forth. And in writing problems, if a question awards 5 marks, you should provide about 5 writing points, like 5 arguments, stuff like that. Okay, so question 1. The brightness of a star depends upon its luminosity, and you will be tempted to think that A is correct, the core temperature, but that's Stefan Boltzmann's law about luminosity, so that's not the answer. The answer is B, the distance from the observer. I'm sorry. So brightness is luminosity over 4 pi d squared, right? So this is what they mean by brightness. Okay. It's what is usually called as intensity. Okay, so don't fall for it. Question 2. Two containers are filled with gases A and B. The gases have the same temperature, but the mean squared speed of the molecules in B is twice the mean squared speed of the molecules in A. Excuse me. Which of the following is equal to the mass of molecule in B over the mass of a molecule in A? I'm gonna need a clean page for this because there is not enough space. So in general, 1/2 m times the average squared velocity of a molecule is equal to 3/2 kT. Okay, so it's proportional to its temperature. So we can simplify the 2 there and solve for c squared, okay, which is equal to 3 kT over m. Okay, and now the information is that the average squared velocity of B is 2 times the average squared velocity of A. Okay, now let's plug in. The temperature is the same, so we have 3/2. Don't know why I got so confused. So 3/2 kT over mb is equal to 3/2 kT over ma times 2. Okay, so 3/2 goes away, kT goes away since it's the same temperature, and we can easily see that ma is twice mb. Okay, so the correct answer is B again, because they are asking for mb over ma, which is exactly 1/2. Okay. Question 3. The average density of the universe is unknown. Scientists believe that there is a critical value for this density. Which of the following describes the future of the universe if the density of the universe is more than the critical density? Okay, so let's read the answers. Option A says it will eventually reach a maximum size. It's kind of true, but it will start contracting. Okay, so A is not correct. It's only partially correct. B, it will keep expanding forever. That will be the case if the density of the universe is less than the critical density. C, it will maintain its present size. This will be the case if the critical density is equal to the density, okay? And then D, it will reach a maximum size and then contract, which is the correct option. All right. Okay, now question number 4. A student used a detector and counter to measure the background radiation count for 5 minutes. He used this value to calculate the background count rate. Which of the following would increase the accuracy of the student's value for the background count rate? Decrease the counting time to 1 minute. That will decrease the accuracy. Increase the counting time to 10 minutes. Okay, this is promising. C, repeat the count with a different detector and calculate the mean value. That's not something you would do because the new detector will introduce new variables into this, so no. And then D, repeat the count in a different location and calculate the mean value. A different location will have a different background rate. So no, the answer is B. 5. A sample of radioactive material has a known half-life. Radioactive decay is a random process. Which of the following predictions can be made? This is a tricky question. A, when a given nucleus will decay? No. B, the time for the whole sample to decay. It's a random process, so no. C, the next nucleus that will decay. That's impossible. We're talking about 10 to the 24. Sorry, 10 to the 23 nuclei in a sample, so no. And then D, the fraction of a sample that will decay in a second. This can be predicted, actually. Okay, because the radioactive decay law tells you that n is n naught e to the minus lambda t. Therefore, the fraction of the sample that will decay is n over n naught. And it can be calculated by just finding the value for that exponent, okay? 6. A piece of chocolate is heated at a constant rate. The graph shows how the temperature of the chocolate varies with time. Select the correct statement for the time between x and y. Okay, another tricky question. Option A. The internal energy of the chocolate increases. Okay, this is a strong candidate because the internal energy, if we call it U, is equal to the kinetic energy plus the potential energy. Between x and y, the potential energy, increases because we are breaking the bonds. Okay, this is the phase when the chocolate melts. So we increase the potential energy by melting, by destroying the bonds. Okay, the kinetic energy is constant because the temperature is constant. So A is a candidate. B, the internal energy of the chocolate stays constant. No, because we increase the potential energy. C, the kinetic energy of the molecules in the chocolate increases. No, because the temperature is constant, so the kinetic energy is constant. And D, the potential energy between the molecules in the chocolate stays constant. No, because we actually increase the potential energy. So the correct option is A. And since this is a nice graph, maybe it's worth saying that in this region, the kinetic energy is constant and the potential energy increases. In this region, the potential energy is constant and the kinetic energy increases. The same goes for this region. Okay, let's move on. 7. The Hertzsprung-Russell diagrams W, X, Y, and Z below show a star cluster at various times when the star cluster is in different stages of evolution. Which of the diagrams represents the cluster in the final stage of evolution? Okay. So in the final stage of evolution, let's examine them one by one. So this one doesn't have a lot of main sequence stars, but it has many stars that are red giants, and therefore it's not in the final stages, because in the final stages you wouldn't even have red giants because they will eventually become dwarfs or black holes. Then diagram X, you have many main sequence stars, so that's wrong. But diagram Y is promising because you don't have lots of main sequence stars, because this in this area that I mark with X, The surface temperature is large, meaning that these stars burn their hydrogen really fast. So these main sequence stars live, that I mark with O, live for a long time because they have a low surface density, and the fusion process is slow. These stars live for um, dozens of billions of years. Okay, so they exist. So we don't have any giants, meaning that they turn into dwarfs. So that's actually the correct answer, because diagram Z is a very weird diagram because you have many main sequence stars, no white dwarfs, no red giants. No, it's actually not weird. This is a young cluster. Okay, so diagram Z is a very young cluster. You only have main sequence stars. So the correct answer here is C. Okay, diagram Y. Okay, I hope I make sense. Okay, question 8. A student investigated the absorption of gamma radiation by lead as shown. With no absorber, the intensity of radiation was I naught. With an absorber of thickness 3.2 centimeters, the intensity was 0.25 I naught. What thickness of material will give an intensity of 0.5 I naught? So you can answer this question really fast and saying that, okay, if 3.2 centimeters reduce the intensity to 0.25 I naught, then for 0.5 I naught, we need 1/2 of that thickness, which is option C, okay? So you can solve it in 1 second like that and move on, but I'm gonna show you the math actually. For those of you who have trouble with this kind of concept, right, the long process of proving this is that, let me use a clean page. The general rule for absorption is that I over I naught is e to the minus mu times x, where mu is a characteristic of the material. Okay, so if 0.25 I naught is left, we have 0.25 I naught over I naught is equal to e to the minus mu times 3.2, right? So therefore we have that e to the mu times 3.2 is 1 over 0.25, which is 4. So mu times 3.2 is ln of 4, which means that mu is ln of 4 over 3.2, which is 0.43 centimeters to the minus 1. And then we apply this once more, knowing that we need I over I naught to be equal to 0.5. And this will happen for mu is calculated, so we can plug it in. So e to the minus 0.43 times x prime, that's the thickness we are looking to find. So x prime is ln of 2 over 0.43 or 1.6 centimeters, okay? So this is the long proof of the same thing that you can do in a second, just by observing this simple proportionality, okay? Questions 9 and 10 refer to the information below. The graph shows how the acceleration a varies with time t for an object undergoing simple harmonic motion. The following graphs show how the other quantities for the object may vary over the same time. Question 9, which graph shows the variation of displacement with time? Okay, so for this one, we recognize that A is minus omega squared x. So if that's acceleration, x is going to be the negative of A over omega naught, right? Yes. Therefore, it's going to be the reverse of this, which means that it's going to look like this. Okay, so which graph is that? It's B. Okay, let me erase this. And then question 10, which graph shows the variation of velocity with time? Okay, the way I do it to do this fast is to take the gradient near zero, near time zero, and then you immediately see that this gradient is negative, right? Therefore, the initial velocity is negative, and it's also a velocity, therefore it's shifted. So by pi over 2. So it's C. Okay, I hope this makes sense. I did a little bit fast. If you want the math for part 10, V is dx over dt. Okay, so it's gonna be our x, it's that quantity over there, so it's minus a over omega squared dx over dt, and then from B we see that that our x is proportional to minus sine omega t, right? So dx over dt is simply minus cosine omega t. Okay, and I think this is unnecessary over here because it creates confusion. So this is a better explanation, okay? So x is proportional to minus sine omega t because, why? Because the sine is, the acceleration looks like a sine function, therefore the displacement is minus a sine function, and then the derivative of a sine is a cosine, so C is the correct answer. All right, now section B. So you see one of the differences with this so-called 5A or 4A or these types of tests, they don't have a space for you to write. So I wonder if this is some sort of an experimental version. So anyway, let's do this. Question 11. The Earth is 81 times more massive than the Moon. The gravitational field strength at the surface of the Earth is 6 times greater than that at the surface of the Moon. Calculate the mean radius of the Moon, and they give you the mean radius of Earth. So let's start the clean page. So they say that the mass of the Earth is 81 times the mass of the Moon. The gravitational field strength at Earth is 6 times the gravitational strength at the Moon. And the radius of the Earth is 6.37 times 10 to the 6 meters, right? So we will start with this. Okay. The definition is that G is G times the mass of the Earth over the radius of the Earth squared, and this is equal to 6 times G mass of the Moon over R of the Moon squared. Okay, G goes away, so we have a really nice cancellation over there. Then the mass of the Earth is 81 times the mass of the Moon. The radius of the Earth, we need it, so we'll keep it, I'm sorry. So R Earth squared, and this is 6 mass of the Moon over R of the Moon squared. So mass of the Moon cancels, so R Moon squared is 6 over 81 R Earth squared. So R Moon is the square root of 6 over 9 times the radius of the Earth. And if you do the math, you will find 1.73 times 10 to the 6. 10 to the 6 meters. Okay. And yeah, this is our answer. We can. Okay, this is strange now because they don't leave you space to work, so we will have to go back and forth. So, question 12. Light from either end of the sun's diameter is analyzed and compared to light from the center of the sun. A hydrogen line in the light from the center of the sun has a wavelength of 490 nanometers. The shift in wavelength observed from opposite edges of the sun's diameter is 3.4 times 10 to the negative 3 nanometers. Calculate the angular velocity of the sun. The radius of the sun is 7 times 10 to the 8 meters. So I'm gonna go back to my clean page. We will actually need a new one. So this is gonna be question 12. Okay, so they say that the lambda, the wavelength at the center, is 490 nanometers. The change in lambda observed is 3.4 times 10 to the negative 3 nanometers. The radius of the sun is 7 times 10 to the 8 meters. Okay, so we will calculate the Doppler factor pretty much, okay, for this scenario. So delta lambda over lambda. And the picture is that as the sun rotates, okay, it creates this shift. Okay, that's the idea. Let me erase this. So delta lambda over lambda is V over C. So V is C times delta lambda over lambda. So this is equal to 3 times 10 to the 8 times 3.4 times 10 to the negative 3 over 490. So we find 2081.6 meters per second. And then the angular velocity can be calculated by using V equals omega r. So omega is V over r, or 2081.6 over 7 times 10 to the 8, which yields 3 times 10 to the negative 6 radians per second. And this was question 12. Okay. Now again, this awkward thing of going back and forth. So question 13, it's a 4-mark question. The graph shows how the binding energy per nucleon varies with nucleon number for a range of isotopes. Explain why fission reactors use isotopes such as uranium-235 as fuel and why there is still ongoing research to develop fusion reactors. Your answer should include reference to the graph. Okay, this is kind of like an open-ended question. It's a little bit of a weird question, but let's start. So this is question 13. So we can write that massive nuclei such as uranium-235 have a lower binding energy per nucleon than the fission products. And we can see this from the graph. So if uranium-235 breaks into two approximately equal products, they will be up here, okay, around the mass number 120, okay, because 120 times 2 is 240, so yeah, close enough. So you see that there is this gap in binding energy per nucleon in favor of the products. Therefore, that's available energy for fission, from fission, okay? So we can write that down. If the binding energy per nucleon for the products is about 1 MeV higher than uranium-235 as seen in the graph. Okay, this means that approximately 235 MeVs of energy per nucleus is available. Okay, for low mass nuclei, for example, hydrogen-2, also known as deuterium, we can fuse them into helium-4, right? Helium-4 has approximately 6 MeV more binding energy per nucleon than hydrogen-2 as seen in the graph. And I can go to the graph and show you. So Deuterium is over here. It has a binding energy per nucleon of about 1 MeV, whereas helium-4 is up here. It has about 7 MeVs per nucleon. So there is a 6 MeV per nucleon gap if this reaction happens. Okay. So if 2 hydrogen fuses 2 times 2 nuclei of hydrogen 2 fuse into 4 helium, we will get 24 MeVs per fusion. Okay, but this is under development. Okay, so fusion, the joke is that fusion, nuclear fusion, is always 10 years into the future. Okay, so fusion is still not feasible because you need high pressure containment and high temperature, which are hard to achieve in a lab setting. Okay, I mean there has been a lot of research. Tokamaks are one field of research towards that direction, and also there are laser ignition facilities that try to create fusion, but still it's not commercially viable. Okay, right. Question 14. Cocoa powder, milk, and hot water are mixed together to produce a hot chocolate drink. The mass of the drink is 275 grams and its initial temperature is 71.5 degrees Celsius. Ice at 0 degrees Celsius is added to the drink to reduce its temperature. Research indicates that the maximum serving temperature of any hot drink should be 58 degrees Celsius. Deduce whether 4 grams of ice will be enough to bring the temperature below 58 degrees Celsius. And they give you the specific heat of ice, the specific heat capacity. They give you the specific latent heat of ice, the specific heat capacity of hot chocolate, and the specific heat capacity of water. All right, let's start a new clean page. So we have 275 grams of hot chocolate at TI, the initial temperature, 71.5 degrees Celsius. We need the final temperature to be 58 degrees Celsius. So therefore, we add ice. So we add 4 grams of ice. Okay. To melt 4 grams of ice, okay, sorry, there is no plural. There is no plural for ice. Okay, so to melt 4 grams of ice, we need, let's calculate the energy needed. Let's call it E. Melt is equal to the mass times the latent heat. The mass is 4 grams, so 4 times 10 to the negative 3 kilograms, times the value they give us, 3.34 times 10 to the 5. So this yields 1,336 joules. Okay, to raise the temperature of water, assuming it melt, okay, of water from 0 degrees Celsius to 58 degrees Celsius, we will need E water, okay, it's gonna be equal to C times M times delta theta. C is 4,190, the mass is still 4 grams, 4 times 10 to the negative 3, and delta theta is 58 degrees, right? And again, when we work with energy needed to raise the temperature of a material, delta theta can be taken, delta theta in Celsius is the same as delta theta in Kelvin. But in general, when you work with temperature, it's safer to convert to Kelvin. Okay, so the energy of water we need is 972.1 joules. Okay, so in total, we will need E total equal to 972.1 plus 1336, which yields 2308.1 joules. Okay, this energy needs to be taken from the hot chocolate. Okay, so let's see. If we apply C times M times delta theta to the hot chocolate now, C is 3,750. The mass is now 0.20, 275 kilograms. And then the initial temperature is 71.5. And by adding this ice, we will go down to some final temperature, right? And this whole thing, since we will need this much energy to melt the ice and also raise its temperature to 58, okay? If we take this energy away from the hot chocolate, this expression is going to be equal to this energy, right? 2308.1 joules. Okay, and if we solve for this, we will find that 71.5 minus TF is 2.24. So the final temperature, if we add 4 grams of ice, the final temperature of the hot chocolate will be 69.3 degrees Celsius. Way higher than the 58 that is required. So no, okay? So 4 grams are not enough. And that's the answer. Another way you can go about this exercise is to find how much ice will be enough, but I mean, we went with this way, so that's good enough. Question 15. A weather balloon takes scientific equipment high into the atmosphere to monitor atmospheric conditions. A weather balloon is filled with hydrogen at a temperature of 22.5 degrees Celsius and a pressure of 1.02 times 10 to the 5 pascals. The volume of the balloon is 7.5 cubic meters. The balloon rises through the atmosphere to a maximum height. At the maximum height, the temperature of the hydrogen in the balloon is minus 48 degrees Celsius and the pressure of the hydrogen in the balloon is 8.4 times 10 to the 4 pascals. Calculate the calculate the volume of the balloon at the maximum height. So let's start with that. So let's create another clean page. So this is question 15. So we are told that the temperature is 22.5 degrees Celsius. The pressure is 102 times 10 to the 5 pascals. And the volume is 7.5 cubic meters. Okay, and then we will raise up in the air and the temperature is going to be minus 48 degrees Celsius. The pressure will drop to 8.4 times 10 to the 4 pascals. Okay, so for A, the initial pressure times the initial volume is N times K times the initial. So this is Ti and this is Tf, so initial and final. So we need to find the number of particles first, okay, because it's not given to us. So N is going to be Pi Vi over K Ti. So that's 102 times 10 to the 5 times 7.5 over K is 1.38 times 10 to the minus 23 times the initial temperature is 295.5 Kelvin. Okay, we need to convert by adding 273. So 295.5, and then the number of particles is 1.88 times 10 to the 26th. Okay, now let's see the second question. Calculate the decrease in the mean kinetic energy of a hydrogen molecule in the balloon as the balloon rises to the maximum height. Wait. I'm sorry, I went a little bit too fast. We calculated the number of particles, but we still haven't calculated the final volume. Okay, to find the final volume, P final times V final is NKT final, where we assume that the number of particles stays the same, right? So now we need to solve for V final, which is NKT final over P final. So that's 188 times 10 to the 26 times 1.38 times 10 to the negative 23rd times 225, which is the final temperature. Minus 48 is 225 kelvins, okay? Over 8.4 times 10 to the 4, so we get 6.93 cubic meters, okay? And now it's time for the question B, and they ask what the reduction in the kinetic energy of the of one molecule is. So the average kinetic energy is simply 3/2 kT for one molecule. Okay, so the change in kinetic energy is simply 3/2 k and then delta t. So we have 3/2 k. 3/2. Let's plug in 1.38 times 10 to the negative 23rd, and then delta T is minus 48, which is the final temperature, minus the initial temperature, which is 22.5. So the change in kinetic energy is minus 1.46 times 10 to the negative 21 joules. Okay, small. Okay, this was question 15, I believe. Okay, yes, the next question is 16. It's a long writing problem with 6 marks. Again, whenever you see this, it means that you have to write about 6 arguments for or against the statement they ask about. Right, a scuba tank is used to store air at high pressure. Explain why the pressure of the air inside the scuba tank increases as the temperature increases. Your answer should refer to the motion of the air molecules. Okay, let's create a clean page. So first, okay, let's write, this is question 16. Okay. So the first point is that as the temperature increases, the kinetic energy increases for the molecules. Okay. Then the RMS speed of air molecules increases. Okay, when molecules collide, with the walls of the tank, of the tank, delta P, the change in momentum, increases as well, because momentum is proportional to velocity. Therefore, if velocity increases, delta P increases. Okay, so since V increases, the velocity, not the volume. Okay, since the velocity increases, okay, the frequency of collisions is higher. Okay, so delta P over delta T is larger. Okay, and since force is delta P over delta T, then force also increases, okay? But pressure is force over area. So if force increases, pressure also increases. And that's the answer if you consider the microscopic motion of molecules. Okay, question 17. A commercial drinks dispenser fills a cup with 0.3 kilograms of water at a temperature of 5 degrees Celsius after chilling it for 2 minutes. Question A. The water enters the dispenser at a temperature of 20 degrees Celsius. Calculate the electrical power of the heater in the dispenser and they give you the specific heat capacity of water. Okay. So, this is 17, question A. So we can use the fact that power is energy over time, right? And energy is Cm delta theta, and then this is over time. Okay, so let me see. I think I made a mistake somewhere. So they say commercial drinks, okay. 5 degrees Celsius after chilling it for, okay, the water enters the dispenser at a temperature of 20 degrees Celsius. Okay, so delta theta is 15, excuse me. So 4,200 times the mass, which is 0.3, times delta theta, which is 15, because the water enters at 20 degrees and chills down to 5, okay? And then this happens in 2 minutes, which is 2 times 60 seconds. So this is equal to 157.5 watts, which you can also write as 158 watts. Okay, I hope this makes sense. And let's move to question B. Suggest why the actual power of the heater may differ from the value calculated in A. Okay, you can put arguments such as energy is transferred to the surroundings, Okay, energy is lost in the cooling dispenser. And you can also say that the efficiency is always less than 100%. Okay, and that's the answer. Moving on to question 18. Superfluid helium-3 has been used as a potential dark matter detector to test the idea. Helium-3 atoms are bombarded with neutrons that use the identity of particle X by completing the nuclear equation in the answer booklet. Okay, so we have a neutron. It has a mass number of 1, 0, zero atomic number. I mean, it doesn't have a charge. Okay, so X should have a proton number of 1, since the other particle is hydrogen. So 1 plus 1 makes 2 to the right hand side, as we have in the left hand side. And then they say it's helium-3, so we just write helium-3. So we have 4 protons and neutrons before, so we need to have 4 protons and neutrons after. So this is tritium, hydrogen-3, and the particle X is just hydrogen. Okay, so hydrogen. Okay, to calculate the total kinetic energy in MeVs of the reaction products, assume that the neutron has 0 kinetic energy, and they give you the masses of the electron, the proton, the neutron, hydrogen 2, hydrogen 3, helium 3, and 4. Okay, that's a lot of information. So the energy is delta E equals to delta mc squared. Okay, so delta m, you have to subtract the products from the reactants. So what I'm trying to say is that you have neutron So you have a neutron, the mass of the neutron plus the mass of 3 helium, okay, plus 2 times the mass of the electron, since they give us the masses of the electron. Let's see if it's actually needed. And why 2 times the mass of the electron? Because helium-3 has 2 electrons, right? The neutron, of course, has no electrons, okay? And then we have to subtract the products, which is the mass of 3 hydrogen, and 1 hydrogen has 1 electron, right? Minus the mass of the particle X, which is just hydrogen, normal hydrogen. And a hydrogen has also 1 electron. So the masses of the electrons are cancelled, actually, so you don't need those. And if we use the values from the table, we will find that this is 8.2 times 10 to the minus 4 atomic mass units, which is equal to 1.3612 times 10 to the negative 30 kilograms. Therefore, delta E is delta mc squared. So this is 1.3612 times 10 to the negative 30 times 3 times 10 to the 8 squared, which is equal to 1.23 times 10 to the negative 13 joules, which is equal to 0.77 MeVs. And to go from this step to this step, we divide by 1.6 times 10 to the negative 19 joules per electron volt. Okay, this was quite long, so let's move on to question B. Tritium hydrogen-3 is an isotope of hydrogen. Define what an isotope is. So let's do this here, Bi. So same atomic number Z, different mass number A. So examples are of isotopes where you have hydrogen, hydrogen-2, hydrogen-3, and then you can have helium-3, helium-4, helium-6, and so on. Okay, so these are isotopes. They have the same atomic number, different mass number. Okay. 2. State what is meant by a positron and suggest why positron emission cannot occur for hydrogen-3. Okay. So the positron has a lepton number of -1 and a charge of +1, and it's the antiparticle of electron. Okay, so hydrogen-3, if it decays into a positron, we will have something like 3 neutrons plus a positron plus a neutrino. So this will be an equation that kind of makes sense, but it violates mass energy. So violates mass energy. Okay, because 3 neutrons, let me see, do they have it here in the table? I'm sorry. Here. Okay. So 3 neutrons are actually heavier than hydrogen-3, so that's impossible. So this situation violates mass energy. Okay. C. Tritium has a half-life of 12.5 years. At a particular instant, a sample of tritium contains 3.2 times 10 to the 12 atoms. I calculate the activity of the sample at this instant. So I'm gonna do it here. I'm gonna solve this part here. So let's do, first of all, if the half-life is 12.5 years, then the decay constant is ln of 2 over T1 half. So that's 0.69 over 12.5 times 365 days times 24 hours in a day times 60 minutes in an hour times 60 seconds in a minute. So that's 1.76 times 10 to the negative 9 seconds to the minus 1. The activity is given by multiplying the decay constant with the number of nuclei So that's 3.2 times 10 to the 12 times 1.76 times 10 to the negative 9. So that's 5,626.8 becquerels. Okay, part 2, determine the activity of this sample 60 years later. So A is A naught e to the minus lambda t, right? So this is 5626.8 times e to the negative 1.76 times 10 to the negative 9 times 60 years, and then we have to multiply times, I'm gonna go down here, 60 years times 365 times 24 times 60 times 60, and this is still in that exponent, okay? I hope this makes sense. And this is equal to 201.4 becquerels, okay? And random trivia for whiskey, okay? So hydrogen 3 is found as a trace in normal water, right? So maybe you will buy a whiskey that claims to be, I don't know, 100 years old, okay? Now, if you go and test and you find tritium in that whiskey that is claimed to be 100 years old, it means that it's not 100 years old, because the half-life, as you see, is 12.5 years. So in 25 years, half of it is going to be gone, and then in 50 years, a quarter is going to be left, and so on and so forth. So by 100 years, you will have almost nothing left, or very, very few traces of hydrogen 3. So this is a method you can use to test liquids like that. I mean, whiskey and other expensive, like wine and stuff like that. Okay, let's move on to question 19. How do you pronounce that word? I guess Salyut, I guess. So Salyut 1 was the first Earth orbiting space station. It was built by the Soviet Union and launched into a low Earth orbit 50 years ago. A. Salyut 1 orbited at an average height above the surface of the Earth of 211 kilometers. The mass of Salyut 1 is 18,400 kilograms. The mass of Earth is 5.98 times 10 to the 24 kilograms. And the radius of Earth is 6.37 times 10 to the 6 meters. Question I. A textbook claims that that for astronauts in Salyut 1, there will be a sunrise 16 times every day. Okay. Assess the validity of this claim, and they give you that one day is 8.64 times 10 to the 4 seconds. So in these types of questions, you have to actually derive the period of rotation. So let's do it here. So we have the force of gravity, G, mass of the Earth, times mass of the spacecraft over r squared is equal to m omega squared times r. So m cancels, and we have G, mass of the Earth, over r cubed, where I pull this r diagonally down to the denominator, and omega we will convert to 4 pi squared over t squared. Okay, so t squared is 4 pi squared r cubed over g times the mass of the Earth, and we will plug in numbers now and then take the square root later. So this is 4 pi squared, and then r is the radius of the Earth, 6 times 37 times 10 to the 6, plus the height above the surface of the Earth, which is 211,000 meters, and this whole thing has to be cubed. And then in the denominator, we have g, which is 6.67 times 10 to the minus 11. And then the mass of the Earth is 5.98 times 10 to the 24. Okay, so this is equal to this enormous number, 28,210,344.6 seconds squared, and don't forget that we have to take the square root of this to find the period, which is 5,311.34 seconds. Now, if we divide the number of seconds in a day, which is 8.64, times 10 to the 4 seconds, over 5,311.34 seconds, okay, we will find 16.3, which is approximately 16 days. So the claim is correct, okay? Let me make a better 6, so 16.3, 16 days, okay. 2. Salyut 1 made almost 3,000 orbits before falling back to Earth. Calculate the change in gravitational potential energy of Salyut 1 as it fell back on Earth. Okay, let's do this. So the gravitational potential energy at the surface of the Earth is minus gm over the radius of the Earth. Notice that this is independent of the mass, right, of the object, because this is a property of the Earth, okay? So this is equal to minus 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24 over 6.37 times 10 to the 6 meters. So this is minus 62.62 times 10 to the 6 joules per kilogram. Now the potential energy at the orbit, okay, is going to be minus gm over the radius of the Earth plus the height where the satellite is located. Okay, so in the numerator we have exactly the same quantities as before, minus 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24 over 6.37 times 10 to the 6 plus 211,000, okay, and if we do this calculation we will find minus 6.61 times 10 to the 6 joules per kilogram. The change in gravitational potential energy is m times delta V, which is equal to 18,400 times minus 62.62, which is the potential at the surface of the planet, which is the final potential, right? I mean, this is where the satellite ends up, minus of the minus, which becomes a plus 60.61, and don't forget that we have to multiply by 10 to the 6 joules. So the change in gravitational potential energy is minus 3.7 times 10 to the 10 joules. Okay, I hope this makes sense. If it doesn't, let me know in the comments and I will explain further. And then B, Salyut 1 burned up over the Pacific Ocean as it re-entered the Earth's atmosphere. Explain why Salyut 1 burned up. So basically, this is a simple answer. So air drag caused the heating of the space station. Okay, so that's an answer. Okay, because the air drag creates heat and then it burns. Okay. Question 20. The suspension system of a car is a set of springs that allows the body of the car to move vertically up and down relative to the wheels. A car is driven along a long straight road that has a series of speed bumps. Speed bumps are raised parts in a road as shown. Okay. At a particular speed of the car, resonance occurs. The amplitude of vibration of the car body on the suspension system becomes much larger. A. Explain why the amplitude of vibration increases at a particular speed. So the answer is that this part A in this question 20. Okay, so a car is forced into oscillation, okay, at its natural frequency. Okay, and then since it's oscillating at its natural frequency, there is a maximum transfer of energy to the car. Okay. B. A car suspension system can be thought of as a mass spring system. The natural frequency of the system is determined by the force constant of the suspension K and the total mass of the system M. Question I. A car is set into vertical oscillation by applying a momentary downwards force. Show that the frequency of oscillation F is given by that expression 1 over 2 pi times the square root of K over M. Okay, so for B, we have to start by saying that the sum of all forces is equal to minus kx, right? And the sum of all forces is equal to mass times the acceleration, right? So the mass times the acceleration is minus kx. So we can solve for A. A is minus k over mx, and this is equal to omega squared times x, okay? And we have an acceleration that is proportional to the displacement and in the opposite direction. Therefore, this is an oscillating system. And omega squared is k over m, but omega squared is 4 pi squared times the frequency squared. And this is equal to k over m, right? So f squared is 1 over 4 pi squared times k over m. So f is 1 over 2 pi times the square root of k over m. That's the answer. Okay, part 2. A person of mass 75 kilograms steps into the car. The vertical height of the car above the road decreases by 1.5 centimeters. The mass of the empty car is 1,450 kilograms. The car is driven along the road at a speed of 13.4 meters per second. Adjacent speed bumps are at a distance of 14.9 meters apart. Deduce whether resonance will occur. You should consider the car as a mass spring system. Okay, that's quite a lot of information. So let's start with the first piece of information. Then that when a person of mass m, so mg, so when a person of mass 75 kilograms steps into the car, the displacement is 1.5 centimeters. So m times g is kx. Therefore, we can calculate k from this information. So k is mg over x, or 75 kilograms times 9.81 over 0.015. Okay, or k is simply 49,050 newtons per meter. Okay, now we can use this information to calculate the natural frequency. So f natural when the passenger is in the car is 1 over 2 pi times the square root of k, which is 49,050, over the mass, which is 1,450 plus 75 kilograms. So the natural frequency is going to be 0.1 hertz. Okay, if v is 13.4 meters per second and s, the distance between the speed bumps, is 14.9 meters, then we can kind of create a frequency using s is v times t, since the velocity is constant, right? So t is s over v. Therefore, 1 over t is v over s, okay? And 1 over t has dimensions of frequency. So frequency is v over s. And if we plug in the numbers, v is 13.4, s is 14.9. This yields 0.9 hertz. So resonance will occur. And I really hate those speed bumps, by the way. So yeah, if you are going with that speed and the speed bumps are these are 14.9 meters away, then a resonance will occur. Okay. Part C, Explain how damping reduces the large amplitude of vibration of the car on its suspension and how it could be achieved in practice. So let's answer it here. So damping reduces energy by absorbing kinetic energy as heat. It can be achieved by introducing a resistive force. Let me fix this. Introducing a resistive force opposite to the velocity. Okay, that's an answer. Okay. Question 21. Curves A, B, and C show the radiation spectra of stars with three different surface temperatures. Curve A represents radiation from curve B represents radiation from the sun. I state what evidence from the graphs suggests that this might be so. So if you notice, the peak is about, if we take the average of those two values, because they seem to be, this spacing over here is equal to this spacing. So we can calculate this value by taking the average. So 700 plus 400 over 2 yields 550 nanometers, which is the peak temperature of the sun. So lambda max is 550 nanometers, and the peak, not the big, the peak, sorry, the peak is between, okay, let me be more concise, is between 400 and 700 nanometers, like the sun. Okay, now question 2. State with a reason which curve represents a star with a lower surface temperature than the sun. Okay, so the temperature is proportional to 1 over lambda max due to Wien's law. Actually, okay, there's not enough space and I feel uncomfortable. Let's go down here. 2. So lambda max is proportional to 1 over t. So as t increases, right, actually as t decreases, because this is what we want, as t decreases, lambda increases, right? So C has a lower t than the sun. Okay. Question 3. Explain using the graphs how the radiation from the star identified in 2 differs from the radiation from the sun. Okay, the peak is at 700 nanometers, so lambda max is 700 nanometers, so it's an IR and / red star, so it will appear red, not yellow like the sun. Okay, question 4. Determine using curve B the surface temperature of the sun. Okay, so we're going to use Wien's law. So lambda T is 2.898 times 10 to the negative 3. So T is 2.898 times 10 to the negative 3 over the temperature, which is, over the lambda, which we found earlier as 550 times 10 to the negative 9. So if we do this calculation, we find 5269.1 Kelvin for the temperature of the sun, which is our answer. Okay, and final question is 22. This was a long test. Okay, almost 50 years ago, a physicist called Vera Rubin found found evidence for the existence of dark matter from her observations of nearby spiral galaxies. Her observations seemed to contradict Newton's laws. A. Show that the velocity v of a star of mass m in an orbit of radius r about a larger mass m is given by the square root of g times the larger mass m over r. Let's use a clean page. So the force of gravity, so if this is the large mass and this is the small mass, okay, so the gravitational force is the centripetal force, so it's equal to mv squared over r. The gravitational force is simply g times the larger mass times the smaller mass over r squared, and this is equal to m v squared over r. M cancels, these r cancels, so v is the square root of g m over r. Okay, this was 22a. Let's go to b. Stars orbit the center of their galaxies. Most of the visible mass of a galaxy is concentrated at its center. The graph shows how the velocity v of stars varies with distance r from the center of the galaxy. Question I. Sketch on the same graph in the answer book how the predicted velocity of stars varies with distance r from the center of the galaxy. Label it with word predicted. So this velocity is going to be proportional to the square root of 1 over r. So this is going to be, so for a really small distance, you're going to have a really large velocity. So it's going to look something like this. Okay, so this is the predicted. Okay, question 2. Explain how dark matter may account for the difference between the observed velocity and the predicted velocity of stars far away from the center of the galaxy. You may assume that for a star orbiting at radius r, all the matter inside the sphere of radius r acts like a point mass at the center. So we can write that this is question 2. So dark matter provides additional mass, additional mass. Okay, so even despite, this is the correct word, so despite no, what am I trying to say? So even if so since v is equal to the square root of g times m over r, comma, when r increases, m is large enough to keep the velocity high, which is the answer. High and constant. Okay, and the idea is that you have a halo of mass, something like that. So you can read about it in the web. Okay, part C. The exact amount of dark matter in the universe is unknown. Explain how the amount of dark matter might be expected to determine the ultimate phase of the universe. Okay, so let's answer it here. So the total mass of the universe will be higher than the one we know. Okay, so since rho, the density is m over v, the rho of the universe will be higher. Okay, so and then if rho is larger than the critical density, the universe will reach a max size and then contract. Okay, and this was unit 5A. Okay, for some reason there are two unit 5s from January 2026. I still haven't found out why there are two unit 5s, but okay, guys, I mean, the more the merrier. I mean, you have extra material to study and go through. So I hope these videos are useful. And I have to confess that today I filmed two videos. The one I just uploaded, which was Unit 6 from January 2026, and this is Unit 5. It's too much for one day. I don't know if you could tell that I was really tired while filming this, but I hope that I was still coherent enough so you guys find some help. Thank you for those of you who are following. Please comment, like, subscribe, and so on, and see you in the next one. Bye.